Good morning, everyone. At first, I'd like to thank you for your interest in knowing more about the GFRP, the glass fiber reinforced polymer bars. We have seen a lot of engineers that are asking for a presentation like this, especially in the recent few years. They were striving to know more about this material and it's the difference in this material in between the characteristics of the GFRP bars to the steel reinforcement. That's what we are going to cover here, is to highlight the design and construction of the concrete reinforced with GFRP bars or VROD reinforcement. Of course, we'll not be able to cover all the aspects, all the angles in the for the design and construction using GFRP in this presentation. So it's only to highlight the main differences in the mechanical behavior between GFRP reinforcement and the steel reinforcement. So the main objective of this presentation is to know more about this material and its fundamental mechanical properties in comparison to the steel reinforcement, and also the major material-based design aspect per the code requirements. So let me first introduce myself. My name is Khalid Mohammed. I am an engineering manager at Cultural VRODs. I have my PhD from here from Canada in 2015. Then worked a couple of years as a postdoc. Then joined Portal as a design engineer in 2018 until now. So let's get started. And please, I'm putting a lot of equations in my presentation. It's very technical. If you have any question, you can stop me at any time and ask your question. So here are the outlines of the presentation. First, going through a small introduction about what is FRP and what is the main difference in the mechanical behavior between GFRP or FRP and the steel reinforcement. Then highlighting the available design codes, the durability assessment. This is very interesting topic as it's the main advantage of using GFRP reinforcement is the durability. Then we can go through the design criteria in terms of the general requirements, the flexure capacity of ultimate and service limit state, the shear capacity, the development length. Then I prepared at the end a small design example for a suspended gauge slab that we can go through as a design example. So let's get started with the FRP material properties. At first, what is FRP? FRP is a composite material that consists of reinforcing fibers plus resin. We have different types of fibers. We have glass, carbon, armored, and basalt fibers. Apparently, if we mix any of these fibers with the resin, we will end up with GFRP bars for glass, CFRP for carbon, AFRP and BFRP for armored and basalt. And also we have different types of resins. We have nylester resins, we have epoxy, we have polyester. Polyester is used mainly for nanostructure applications, while the Canadian codes are allowing for the use of nylester or epoxy for structural applications. But the US codes are limited only for the nylester resin. So for today's presentation, we will focus on the glass fibers and the nylester resins, or in other words, the GFRP bars. And if we took this GFRP bar and put it under the microscope, we will see this photo in here. So to have a sense of the size of this photo, this distance here is 10 micrometer. And as you can see, the round things here are the fibers. And in between the fibers, we have the black area here is the resin. The main purpose of the fiber in the bars is to provide the mechanical properties, the tensile strength in the direction of the fibers and the main mechanical behavior, while the main purpose of the resin is to apparently to compile the fibers together and also to protect the fibers from any outside attacks, from environmental attacks. We produce different sizes and different shapes of GFRP bars. We have sizes from 6mm bars up to 40mm bars for tunneling applications. We have different shapes, U shapes, L shapes, with different sizes. We have headed end bars, we have smooth dowels, we have CFRP bars. It's very limited now, but we have them. BFRP bars as well, and so on. So this slide explains the main difference in the mechanical properties between GFRP bars and steel reinforcement. So I brought this curve here, which is the stress strain of both materials. The steel reinforcement in red, this is grade 60. It's called grade 60 steel bars. Here in North America, it's grade 60. And for this is the blue line here is for the VROD 60 GFRP bars. And we can see a lot of differences in this curve. First, GFRP bars are linear elastic up to the ultimate strength. The ultimate strength or the ultimate strength of GFRP reinforcement is much higher than the yielding strength or the ultimate strength of the steel bars. For example, for this VROD 60, we have an average strength of about 1300 megapascal, while for the grade 60 bars, we have a yielding strength of 400 megapascal and the ultimate strength of 600. So the tensile strength is about at least double of the tensile strength of the steel rebars. We can also notice that the inclination of the blue line here is less than the inclination of the red line or the red curve before the yielding point, which means that the modulus of the GFRP bars is lower than the elastic modulus of the steel bars before the yielding points. So we have main differences here. The tensile strength is higher than the steel. The tensile modulus is lower than steel. These two characteristics will be reflected in the design process, and they are reflected in the codes as well. Also, the shear strength of GFRP bars is slightly less than the steel. For example, for VROD 60, we have a shear strength. I'm talking about the transverse shear strength. It's about 200 megapascal, while for the steel is 300 megapascal. So it's approximately 2/3. Bond strength is approximately the same or slightly higher than the steel bars. We have an average bond strength of 14 megapascal for GFRP, while for steel reinforcement is between 10 and 8 and 10 megapascal. This is the pull-out strength. So the bond strength of GFRP reinforcement is slightly higher than that of the steel reinforcement. The compressive strength of GFRP reinforcement is currently neglected by most of the codes, even though we know that the GFRP reinforcement, especially for VROD 60, the compressive strength is between 50 to 80% of the tensile strength, which is very high, but currently the codes are neglecting the contribution of the GFRP reinforcement in compression. It's also very important to mention that GFRP reinforcement could undergo creep rupture under sustained loads, and we need to check the creep rupture strength when designing using GFRP reinforcement. And GFRP reinforcement has good fatigue endurance in comparison to the steel reinforcement. So these are the main differences in the mechanical properties between GFRP reinforcement and the steel reinforcement, which again will be reflected in the design process and are reflected in the codes for the design of GFRP reinforcement. Bend bars, this is a very important topic. Well, bend bars, first of all, bend bars are pre-shaped in the manufacturing facility and shipped to the construction site in a pre-shaped profiles. They cannot be straightened up or even reshaped in the construction site once they are produced and cured. So the GFRP reinforcement, the bend bars are shipped from the manufacturing facility with pre-shaped profiles and used in the construction site with these with the required lengths and required shapes as per the drawings. We can manufacture a lot of shapes, a lot of sizes. However, we are limited with the size. For example, if we have a big stair of maybe 2 meter by 2 meter, this is very, very large. So we need to splice it in 2 pieces, and we are going to splice it using the code equations and the lab splice per the code requirements. Also, researchers have been investigating the tensile strength of the GFRP bend bars, and they noted that the GFRP bend bars are the tensile strength of bend bars is a little bit less than the tensile strength of the straight bars. They have been developing testing method to estimate the tensile strength of bend bars. This one is called B5. One of the methods that is developed it's by putting or casting 2 concrete blocks and putting one stirrup in between those 2 concrete blocks, then pushing them away from each other to induce tensile force on the bend portion. And at the end, they noted that in most of the time, the rupture or the failure of GFRP bend bars is happening at the bend portion. And that's why they started to compare the tensile strength of GFRP bend bars to the straight bars, and they found that the bend portion is reducing the tensile strength by 40 to 60%, in average 50%. This is still, if we have 50% of 1300 or even 1100 megapascal, we're still away from the yielding strength of the steel reinforcement. Also, it's important to mention that the bent internal diameter of GFRP reinforcement is 3 to 4 times the bar diameter, which is approximately the same as for steel reinforcement. This slide, in most cases, I'm not going to present this slide. This is but let's speak about it. This is the main benefits of using GFRP reinforcement, and it will give us the sense where to use it. For example, GFRP reinforcement, as we discussed, it has high tensile strength in comparison to the steel reinforcement. GFRP is also corrosion free, which means it doesn't corrode. It cannot corrode. It's fibers and resins. So not unlike steel, it cannot corrode. So we can use GFRP reinforcement in any area when the corrosion is a concern. GFRP reinforcement also is highly chemical resistance, so it's also used in situations where the element is exposed to chemical. The GFRP is non-electromagnetic, non-magnetic, and it's mainly used in MRIs and also in road tolls where the neutrality is important. GFRP reinforcement has lightweight, it's 1/4 the weight of steel and easy to install. So contractors love it because of those two options, those two criteria: the lightweight, 1/4 of steel, and the ease of installation. GFRP has low thermal conductivity, which makes it very attractive in insulated walls and balconies where the element needs some insulations. And also GFRP has low environmental impacts. So again, this will give us a sense where to use it. The main applications for GFRP reinforcement, at least here in North America, is the bridge decks, the box girders, and barrier wall sidewalks for bridge elements. We have MSE walls, retaining walls, culverts. When they are exposed to earth, the earth is putting some corrosion concerns. So GFRP reinforcement is very attractive in these elements. In any element when it's subjected to salt ions, chlorides, or chemicals, Florida is a big consumer of GFRP reinforcement because of these salt ions, chlorides, and chemicals. It's also very attractive in chambers, underground chambers, vaults, duct banks, where also the earth will attack the concrete and the steel reinforcement. And any other element where when the durability is a concern, for example, septic tanks, the manholes, hook grates, and so on and so forth. Let's talk about the design codes. And here in Canada, we have two design codes. We have the CSA, which is the Canadian Standard Association CSA S806, which is the building structure with fiber reinforced polymers. And this is mainly for buildings, from its name, of course. And we have also the S6, which is for the Canadian Highway Bridge Design Code. For the specification, we have the CSA S807. The second edition is 2019, and this is a specification for fiber reinforced polymer bars. And the importance of this document is that it carries the requirement for GFRP reinforcement to be used in construction, such as the minimum tensile strength, modulus, bond strength, shear strength, durability requirements, mechanical, physical requirements, heat rupture strength. So all the manufacturers should comply, their product should comply with this document in order to be used in structural elements. The S807 have requirements for structural reinforcement, vinyl ester resin, epoxy resin, and also for polyester bars, which is for non-structural elements. In the US, we have similar codes. We have the ASTM D7957. The second edition was in 2022. And this is also the specification for GFRP reinforcement in the US. For the design codes, we have the ACI 440. This is for the building, for the buildings. And this year, we should see another edition of this ACI 440, because the latest edition was in 2015. So the committee is working on another edition. Hopefully, it will be released I think in September. And for bridges, we have the Ashton RFD, the second edition in 2018. In this presentation, I'm going to focus on the Canadian Code S806. However, the design process is the same as for any code. The only difference is the limitation and requirements. But if you are interested in any other code, I can give you these limitations or these requirements while presenting. But I'm going to focus on the equations from the S806. So of course, these codes are built based on research that have been started since 1990s. We have a long history of research now. I'm showing here some photos of beams under flexure. We have beams under shear. This is pre-stressed beams with shear reinforcement of GFRP and CFRP stirrups. These are also circular sections under flexure, under shear, columns, rectangular columns, circular columns. Columns have been tested under concentric load, eccentric loads, and so on. Even columns under cyclic loads for lateral resisting systems. Shear walls, small walls, short walls, and all have been tested in labs under cyclic loads for lateral resistance system. And this is underground chambers that also have been tested and is currently being used by Hydro-Quebec in most of their underground chambers. Let's talk about durability. Durability, again, is a key benefit of using GFRP reinforcement, and it's important to mention how the durability of GFRP is assessed. So we have two methods of analysis. We have the laboratory tests and we have the field investigations. The laboratory test is by putting the bars in high temperature, 60, 50 degrees, and in concentrated alkaline solution with a pH of more than 13 for a long period, for 3 months, for 6 months, for a year. Then taking out the material from this conditioning and test them for any strength retention to see if there are any loss in the tensile strength, in the shear strength. Then we can extrapolate the results to expect the strength after 100 years, after 50 years, the service lives that we need. The other method of analysis is the field investigation by extracting samples from existing structures after a long period of exposure to natural conditions. And in this regard, I'm going to highlight two studies, one by the University of Miami in 2017, and the other one by the University of Sherbrooke here in Canada in 2018. The University of Miami extracted samples from 10 different bridges across the US, and the other one by the University of Sherbrooke extracted samples from different bridges across Canada after the one by the University of Miami after 15 years of exposure, and the other one by the University of Sherbrooke is after 18 years of exposures. Both studies put the samples under the microscopes, tested the samples for any strength retention, and they didn't see any degradation of the material after this time, after 15 years, after 18 years. The University of Miami reported a degradation of less than 3%, while the laboratory assessment, laboratory tests suggesting that there should be some degradation of the material after 15 years or 17 years of exposure. And both studies highlighted how aggressive the laboratory tests are. However, most of the codes, or all the codes now, are based on the durability of GFRP bars based on the laboratory tests and for service life performance up to 100 years. Let's talk about the design criteria and first giving some general requirements. The same as for reinforcement, we have some design assumptions. The plan section remain plan after deformation. The ultimate concrete strain is 0.0035. This per the Canadian codes. Per the US is 0.003. Also, the tensile strength of the concrete and the compressive strength of FRP bars are neglected by the codes. As we mentioned before, most of the codes are neglecting the contribution of GFRP reinforcement in compression. GFRP bars is perfectly bonded to the concrete, and the stress strain of GFRP is linear elastic until failure, which reflecting the main behavior of GFRP reinforcement. Design philosophy is the same as for steel reinforcement. We have the design based on the limit state design principle, which is the ultimate limit state and the surface limit state. Material resistance factor, again, the same way as for steel reinforcement, we have resistance factor. For example, for the S806, we have phi F of 0.75. This is for the GFRP reinforcement. And for the concrete, it's 0.65 for custom place and 0.7 for precast concrete. Load combinations, again, all the codes are specifying that the loads and load combinations are the same as for steel reinforced elements. For example, from the Canadian code, we have a load combination at the ultimate limit state of 1.25 the dead load plus 1.5 the live load. So here we have the same calculation for the loads, for the load combinations, for the stresses, for bending moment, for shear force. And after calculating all of these, the designer can decide if the designer wants to use GFRP reinforcement or steel reinforcement. Let's talk about the flexure capacity of ultimate limit state. And at ultimate limit state, we have the same types of sections as for steel reinforcement. We have the balanced section when the actual reinforcement ratio is equal to the balanced reinforcement ratio. And when it's more, so the section is over reinforced section. And when it's less, so the section is under reinforced section. And to calculate the balanced reinforcement ratio, we can use this equation in here. The other way to estimate or to know the type of the section is to calculate the actual strength in the GFRP reinforcement, the FF, from this equation in here, and compare to the ultimate strength. If it's lower, so the section is over reinforced, and if it's more, so the section is under reinforced. All the codes, of course, the balanced section is not allowed by any of the codes, but all the codes are allowing for the over reinforced sections or the under reinforced sections when it comes to the GFRP design. And we have different equations and different requirements for both types of sections. So for the over reinforced section, to calculate the resisting moment, we can use this equation in here. And for the under reinforced section, we have this equation here. The only difference is the FF, and here we have the FF ultimate and beta 1, because here for the over reinforced section, we achieved the maximum strain in the concrete. So the beta 1 will be different. Compared to the under reinforced section, we didn't achieve the strain, the ultimate strain in the concrete. So after calculating the resisting moment, we can compare the resisting moment per the code requirements. For the S806, we have the resisting moment should be more than or equal to 1.5 times the cracking moment. Otherwise, if the cracking moment is more than or equal to 1.5 times the factor of the moment, this requirement can be neglected. For the over reinforced section, the S806 specifies that the resisting moment should be more than the factored moment, and for the under reinforced section, the resisting moment should be more than or equal to 1.6 times the factored moments. Flexure capacity as surface limit state, and it's very important to mention here that we need to check the flexure capacity as surface limit state when it comes to the design using GFRP reinforcement. And this is because GFRP reinforcement are having higher tensile strength than the steel reinforcement, which will lead to higher ultimate capacity, higher resisting moment in comparison to the steel reinforcement. So in most cases, the flexure design at ultimate limit state is satisfied in comparison to steel. But also GFRP reinforcement are having lower elastic modulus compared to steel reinforcement, which will induce more cracking, more deflections. So we need to check the flexure capacity at surface limit states when it comes to GFRP design. And I would say that in most cases, in 90% of the cases, the design of the GFRP reinforced element is controlled by the flexure capacity at surface limit state. So at surface limit state, we need to check at least three things. We need to check the strength of the GFRP reinforcement at surface to avoid the creep rupture of the GFRP bars. We need to check the crack width. Well, the crack width at for steel reinforced elements is restricted to avoid the corrosion of the steel reinforcement, but here the corrosion is not a concern. But still, the crack width is undesirable for aesthetic reasons only. Deflections, we need also to check the deflections and compare them with the same limits as for the steel reinforced elements. As you know, for the flexure capacity at surface limit state, the depth of the neutral axis is equal to K multiplied by D, and this K is from this equation in here based on the reinforcement ratio and the modular ratio. And at the surface limit state, we can use the cracking moment of inertia based on this equation in here. So here are the requirements for the flexure design at surface limit state. For the strength of the GFRP bars at surface, we can estimate the FFS from this equation in here, and it should be less than or equal to 0.25 of FF ultimate. This is per the Canadian coast, 0.3 per the ACI, not the ACI, the AASHTO, and the new edition of the ACI will be 0.3 as well. The crack width, again, per the S806, the crack width is calculated from the Z factor, which is the stresses across the crack, based on this equation in here, which is the same equation as for shear reinforcement, except that we have another coefficient, a new coefficient here, the KB, which is the bond bending coefficient. And we have been doing a lot of research on this KB, and we arrived at a KB equal to from 0.8 to 0.9 for VRODs. Deflections are calculated the same way as for shear reinforced elements by using the cracking moment of inertia per the S806, and per the ACI and the AASHTO is based on the effective moment of inertia. Shear capacity. Again, we have the same shear strength as for the shear reinforced elements. The VR, the shear strength, is equal to the summation of VC plus VF, and VC is the concrete contribution to the shear strength, and VF is the shear reinforcement contribution to the shear strength. However, the S806 specify that this VR should be less than or equal to this equation in here. So we have this equation to calculate the VC, the concrete contribution to the shear strength. I'm not going into details about the terms of these equations, but only to highlight the equations, and if there's any big difference between the steel reinforcement and GFRP reinforcement, it's only to highlight this difference. So we have this equation for the concrete. We have some coefficients here, Kr, Km, Ka, Ks. Again, this is very similar to the steel reinforced elements, and VC is limited between 0.11 of this equation to 0.22 of this equation. Shear reinforcement contribution is according to this equation. Again, this is the same equation as for shear reinforcement, except that for FF ultimate, it's limited to the tensile strength of the bent portion of the bent bars of the stirrups, or should be less than or equal to 0.005 of the modulus of elasticity of the GFRP reinforcement. And this is to avoid the cracking of the concrete when using GFRP reinforcement. The minimum shear reinforcement, the S806 specify that when the ultimate shear is more than half of the VC, this except for slab and footing, we need to provide minimum shear reinforcement based on this equation here, and the spacing of this reinforcement should be 0.6 the shear depth dV, or 400 millimeter. Development length, we have the same, again, we have the same equation as for shear reinforcement, and this equation in here, and we have some coefficients here, except maybe of one coefficient. I think this is for the fiber type, which is K4, it's equal to 1 for GFRP reinforcement. However, we can expect that the splice length or the development length of GFRP reinforcement to be longer than that of the steel reinforcement, because in the equation we have FF here, which is the tensile strength of the GFRP reinforcement, which is much higher than the tensile strength or the yielding strength of the steel reinforcement. And all the codes are specifying that the slab splice, the splice length shall be 1.3 times the development length based on this equation in here. Let's go to the design example again. This is a suspended garage slab that we have been designed recently using GFRP reinforcement, and this slab is 200 millimeter thickness, and it's approximately 7.2 meter by 6 meter. It's irregular in shapes, and we designed this slab based on the Canadian code S806. So first step is to calculate the design moments. First, to calculate the loads. So we took the loads from the National Building Code of Canada, the NBC the latest edition 2015. Then the load combinations, again based on the NBC 1.4, the dead load, this is the ultimate, or the other one is 1.25, the dead load plus 1.5, the light loads. And for the service, we assume that the service load is equal to the dead load plus the live load. And because the slab was irregular in shape, we used finite element modeling to calculate the bending moment at ultimate and at service. So here, a part of this, or the finding of the finite element modeling. So the bending moment at ultimate was 35.6 kilonewton meter per meter, and at service 24.8 kilonewton meter per meter. First, to choose the material, we used VROD 60 20 M bars, 20 millimeter bars, with an ultimate tensile strength of 1100 megapascal and a modulus of 60 gigapascal. The diameter of the bar is 20 millimeters, and the area, the cross-section area of the bar is 284 square millimeters. 5-factor per the code is 0.75 for the GFRP reinforcement. FRP was 25 megapascal, and we used 50 millimeter as a concrete cover, so the depth was 143 millimeter. So first step is to assume the reinforcement. We first calculated the minimum reinforcement for shrinkage and temperature, which is 0.0025 the area of the section, B by H, which is 508 square millimeter. So we used VROD 60 20 M bars, 20 millimeter bars at 200 millimeter spacing, which gives about 1400 square millimeter. Then we change the capacity at the Flexure at the ultimate limit state. First, we calculated the actual strength with the GFRP reinforcement. It's about 490 megapascal, which is much less than the ultimate strength of 1100. So apparently the section will be over reinforced section. The balance reinforcement ratio is 0.004. So the section is compression controlled or over reinforced section. We calculated the resisting moment 64 kilonewton meter per meter. This is approximately double the bending moment at ultimate, which is about 35 kilonewton meter per meter. Cracking moment, we calculated the cracking moment 20 kilonewton. This should be multiplied by 1.5 and compared to the resisting moment. So apparently by multiplying this by 1.5, it's about 30. So it's much less than the resisting moment. The flexure capacity at service limit state, and first calculating the factors K and I crack. Then the strength at the service limit state, the FFS, which was about 131 megapascal. This is much less than the 0.25 of FF ultimate, which is 275 megapascal. The crack width. So as you can see here, we calculated the crack width G factor, which is 44.3 or 44,400 Newton per millimeter. This is very close to the requirement of the S806 of 45,000 Newton per millimeter. And as you can see, the section design was controlled by the crack width at the service limit state. Deflection, because it's a suspended slab, so we had to calculate the deflection at the short-term and the long-term deflection. So we first calculated the deflection per the dead load only, 10 millimeter. Then the live load, about 36 millimeter, which is lower than the requirement of 39 millimeter. Then we calculated the long-term deflection per the sustained load, and here the sustained load is assumed the dead load plus 20% of the live load. So we calculated the deflection, the long-term deflection, which was about 25 millimeter. This is again less than the requirement of 29.6 millimeter. Then the shear design. First, we calculated the DV, which is the shear depth. It's a maximum of 0.9 the depth or 0.72 of the height of the section. Then we calculated the shear forces from the from the finite element modeling. And the critical section per the S806 is at a section DV from the support, and in that case it's the wall edges. So the VF was 54 kilonewton, and MF, the bending moment at the same section, at the same critical section for the shear, is 9 kilonewton meter. Then we calculated the VC, which was about 104 kilonewton per meter. So the shear strength was okay. So we did the detailing of this slab using the S806, how the reinforcement is anchored to the walls, calculating the minimum reinforcement in the top, and also calculating the bending moment or the reinforcement for the negative bending moment. So as you can see here, this is a summary of the reinforcement. As a main reinforcement, we use 20 M bars, VROD 60 at 200 millimeter on center. For the top reinforcement, 12 millimeter bars, VROD 60, VROD 46 here in that case, at 250 millimeter on center. And for the negative bending moment, we used some additional reinforcement in this area because we had a high bending moment, high knee bending moment in this corner here. So we used 15 millimeter bars, VROD 60 at 150 millimeter on center. I didn't include the applications, Mario, on my presentation, but I can show them right now if you'd like to go through them.
Sure. Well, that's of course, if it is of interest to everybody. I don't mean to be presenting some of the projects that we've gone through. If you've already gone to our website and looked up some of the projects that we have on there, it's pretty much the same thing. Major projects, the Cable State Bridge in northern Ontario. We have the aluminum smelters in there. So just a few of the most important projects that we've worked on. I guess our website is probably the best source for that type of information. I would probably leave that time more for the questions that the people might have that are attending this presentation, instead of going through projects. That's okay with everybody.
Sounds good, Mario.
Yeah, sounds good.
Thank you, Khalid.
Well done, thank you.
It's fantastic. Thank you. If you can stop presenting, Khalid, that'll be great. And then we'll throw it around the room if anyone's got any questions.
Yeah, I've got a couple of questions. Okay, so let's see. Going through my list of questions. Creep rupture. So one of the things that was kind of raised was long-term creep, and it was kind of discussed very briefly. But I'd like to know a little bit more about what the design requirements around creep rupture and what's the if you like the long-term issues that maybe in line with that issue.
So let me put my screen again. I'll be back to the. So creep rupture is here. It's the strength of the GFRP bars at service. Creep rupture, well, researchers have been putting the GFRP bars under sustained loads and monitoring the rupture time of the GFRP reinforcement, and putting different load levels, 90% of the ultimate load, and measuring the time or estimating the time until the bar is rupturing, 80%, 70%, and so on. Then extrapolating the results in a linear manner in a log scale to expect the creep rupture limit after 100 years, 50 years, and so on. Then applying a safety factor. The ACI is applying 1.6 as a safety factor to extrapolate the results and expect the creep rupture limit after 100 years. And that's why we have this equation or this requirement. This is not a requirement for steel reinforcement, but for GFRP reinforcement, it is a requirement, is to calculate the strength of the GFRP reinforcement. I wouldn't say at service limit state, because at service we have the full live load. But for example, the ASH2 is specifying that the bending moment here should be dead load plus 20% of the live load. And then the ASH2 is specifying that this limit, the strength of the GFRP reinforcement, should be less than or equal to 0.3, which is 30% of the tensile, the ultimate strength of the GFRP reinforcement. And this is to account for the creep rupture strength after 100 years.